Guess we're going solo on this as the moderator, so I'll go ahead and get started. My name is John Nations. I'm at LSU Museum of Natural Science, and this is a project I've been working on with some colleagues at Museum of Victoria in Melbourne, Australia. So, kind of a fundamental tenet of biology is that phenotype is influenced by the environment that the organism lives in. And over the past few centuries that we've been working on this sort of thing, we've realized that some traits actually seem to be more labile than other traits. For example, body size seems to be particularly labile, and is often associated with the ecology or the environment that the organism is living in. And a classic example of this is Bergmann's rule, which you're probably mostly familiar with, and this is saying that there's some kind of selective advantage conferred for thermoregulation for the environment, for the animal in its environment. This is generally talking about homeothermic animals, although sometimes they're heterotherms as well. And saying that has to do with the surface area ratio to body size, but generally in colder climates, animals are larger, and in warmer climates, they're smaller. And this has received a lot of support throughout the past 100 years or so, but a lot of studies have not found strong support for this. And so there's been a few other proposed hypotheses, one of which is the resource rule, which sort of says it's actually not really the temperature, but maybe the available resources that the organism has that affects the body size. So Australia is a really cool place to think about these kind of questions. It's defined by this really strong coastal to interior gradient. So you get much wetter areas around the coast of the continent, and then a very, very dry interior. And so this can be broadly partitioned into 4 biomes. And so we have our arid region in the middle, here in yellow. The red center is often cold, and this is extremely dry desert. And then it's surrounded in green here by these mesic environments. And these are often a little bit cooler, definitely higher precipitation. And some of these areas actually include regions that can be classified as temperate rainforests. And then in the north, we have the monsoon tropics in purple. And these are defined by seasonality. So part of the year it's extremely dry and arid, and the other part there's just a lot of precipitation. There's actually a temperate rainforest portion of Australia, but that won't play into our story today. So again, Australia is really defined by this arid region in the middle, and this is thought to have began around 15 million years ago. But in the past 15 million years ago, there's been massive climatic fluctuations, and this dry center has compressed and expanded and fluctuated many, many times throughout Australia's history for the past 15 million years. Of course, Australia is known for charismatic marsupial fauna, but there's actually 2 radiations of native mice and rats. One of these, the older radiation that occupies Sahul, so this is New Guinea and Australia. One group, the Pseudomys division, this clade has actually colonized most of mainland Australia in the past 5 million years. And this includes the genera Pseudomys, Legadina, Masticomes, Notomes, and Zizimes, normally called the Pseudomys division. And as you can see from these illustrations, there's actually quite a bit of variation, not only in size, but also in phenotype. So this Pseudomys division has actually repeatedly colonized these arid, monsoon, and mesic biomes throughout the history, or throughout the past 5 million years. This has created some really cool patterns. Like you often get these species-paired groups where one sister species occupies maybe the arid biome and one occupies the mesic biome. And then also these other younger clades where there's 3 or 4 species, and these will occupy 2 or 3 biomes between those 3 species. So it's a cool group to ask if there's parallel evolution of phenotypic traits associated with these environments. So specifically here, we're going to ask, across all these biomes, which, if any, environmental variables predict body size. And then we're going to ask, in general, can body size be predicted by these biome associations? So to look at environmental predictors of body size, first we assembled body mass data for 31 of these Pseudomys species. So there's lots of ways of estimating body size. Some people may use skull size or snout vent length or something like this. Here we're using body size as our metric, or body mass as our metric for body size. And I may use these interchangeably sometimes. For these 31 species, the body mass range is between 8 grams and 135 grams, so pretty large. We also assembled 19 environmental variables for these 31 species using this online database, the Atlas of Living Australia. And this is a really cool online repository of observation and other occurrence data for all sorts of Australian organisms. And for each one of these observations or localities, there's a whole slew of environmental variables associated with it. So in this case, for these 31 species, it resulted in something like 30,000 observations of environmental variables for all these. So we removed really highly correlated environmental variables and retained 7 of them. We also added latitude in it. A lot of times people use latitude as a proxy for temperature when they're testing for control. So we wanted to include this as well. So we calculated the log mean and the standard deviation of the log mean of all these variables. We also took advantage of that subclade pattern I kind of explained earlier, where you have these sister pairs that occupy these different biomes, these different environments, and use this in our models, which I'll explain right now. So we fit Bayesian phylogenetic multi-level models in a package called BRMS, and for anyone doing this kind of work, I highly recommend checking out BRMS. It's really cool. It's easy R interface and actually compiles your models in C++ and runs them in scan using Hamilton Monte Carlo algorithm. It's really awesome. So we fit one model for each environmental variable. It's just a basic kind of R format of the model. The only things I'm going to point out here is that BRMS allows you to actually incorporate the mean value and the standard deviation into the model for the particular variable, which is really great because, of course, these animals don't just occupy a single point in Australia that is represented by the mean. They actually, a lot of them have quite large ranges, and we want to include that variance in the model. So we find that temperature is negatively associated with body mass at the 95% credible interval level. You can see that not only from the slope here, obviously going down, but also that our estimate of effect is less than 0. It doesn't overlap 0. So we see no clear effect of latitude on body mass here. Again, that's likely due to perhaps this coastal to interior gradient that we see in Australia. So latitude might not be a very good proxy for temperature in this place. But temperature wasn't the only environmental variable we found that had a strong effect. We also see a strong effect from aridity, exactly the inverse of aridity, and net primary production and precipitation. All these are strongly associated at the 93 to 95% credible interval levels. So this sort of supports the idea that temperature has a strong negative effect on body size, and this is what we would expect for Bergman's rule. Latitude, like I said, doesn't really seem to be a good proxy for temperature here. But we find additional support for this concept of the resource rule, because it's not only temperature, but it's also precipitation, net primary production, and this inverse aridity. So it might be challenging in this sort of environment to really disentangle what, if any, particular environmental variable has the strongest effect on body size. And perhaps none of them very well could be actually a combination of multiple influencing this. So to sort of come to the same question from a little bit different perspective, we actually want to see if these body size are predicted directly by this biome affinity. So we use the same log, we use the same body mass data, and we use body mass classifications from that publication Smith 0 in 2018. And in this model, we actually took 100 randomly sampled trees with a posterior distribution to species tree analysis. They ran, and this is to add in some of the topological uncertainty in their estimation by their phylogenetic hypothesis. Not all these rows are supported 100%. And again, fit this in BRMS. We ran one model per phylogenetic tree, so it's 100 models total. And again, it's just kind of the basic R format of the model. The only thing I want to point out here with this one is that instead of a continuous variable like temperature or something like that, we actually can use this categorical variable habitat here as our predictor. All right, so these are the marginal distributions of the phylogenetically corrected log body mass for each of the biomes. So these marginal distributions can sort of be thought of as silhouettes of the multi-dimensional posterior distribution. And if we wanted to actually do some kind of informal test of significance here, we can't actually just look at the visual overlap between these distributions. We actually need to calculate the difference itself. And that's trivial to do in this case. All we actually do is simply calculate the difference. And if the difference does not overlap 0, we can say with confidence that these things are actually different from one another. So on the far left, you'll see when we subtract the arid or the mesic posterior from the arid posterior, you'll see that we end up with a negative value. Does not overlap 0. That lets us confidently say that, okay, the animals in the mesic habitat are larger than the animals in the arid habitat. We find the same thing for the monsoon habitat. The mesic animals are larger. However, in the middle there, you'll see that between arid and monsoon biomes, the mean is 0. And so this is basically telling us that the body mass of these two is exactly the same. So one of the cool things about doing these sort of multi-level models, these Bayesian multi-level models, is we can actually estimate the phylogenetic signal here, Peebles lambda. This has been outlined in these two publications along with several other sources. And so we actually estimate the phylogenetic signal of Peebles lambda or log body mass. We get an incredibly high value, close to 1 as you can get. This line here is actually our highest posterior density. It's like 0.995. And our mean is in the dotted line, so around 0.92. So this is saying that there's a very high phylogenetic signal in the evolution of body mass in this group. So species in mesic habitats are larger than the species in our arid or monsoon habitats. However, we're getting this signal that body mass evolved in this Brownian manner. This high phylogenetic signal indicates that we have sort of an unbounded random walk pattern for body mass in this radiation. Yet we're still seeing these predictable body size shifts. So kind of what gives, right? Like we're sort of receiving conflicting results of both randomness and predictability. But I think that we have a hypothesis that might explain what's going on here. So again, Australia underwent these really significant climatic oscillations in the Pliocene and Pleistocene. And it's outlined here is we're looking at the sea level fluctuation. And during this time of massive sea level fluctuation, this arid biome is just shrinking and expanding. This mesic biome is shrinking and expanding around it as that happens. And during this time, and this is when the Sidonia division was actively colonizing and radiating in Australia, and they were repeatedly colonizing this arid biome, monsoon biome, and mesic biome. So in 2008, Rebel et al. Published a nice paper where they used a lot of simulated data to look and see what sorts of factors can actually be affecting our estimates of phylogenetic signal. And they found that when they really turned up the fluctuating selection on their trait that they were looking at, they saw just an increase in our estimates of phylogenetic signal. So strong fluctuating selection increases phylogenetic signal, which is exactly what we think is happening in the history of the Sidonia division. Because, of course, they were experiencing very strong fluctuating selection throughout the rapid oscillations of these biome sizes when they're colonizing. So we're actually getting a signal where the environment itself may be changing kind of randomly, but the biome, both the body mass of these animals is changing predictably within this sort of climatic driver. So sort of broader message from this, I think that interpretations of phenotypic evolution may vary depending on which level of the hierarchy we look at. So for example, if we're looking at the evolution of body mass across this group, we may be able to determine, oh, well, it seems to be actually biome dependent and not just random. However, if we're looking at a larger group, let's say all of rodents or all of mammals or something like that, we may not be able to actually pick out that biome effect that's happening. We may actually say, oh, wow, body mass is evolving randomly across a tree or in a Brownian manner. So I think our findings highlight the importance of local patterns of phenotypic evolution when you're examining these macroevolutionary processes at lower phylogenetic levels. All right, that's all I have. I want to thank Smithson for helping to get this project started. My advisor, Jeff Gesselson, Samir Shaka did some illustrations for us. And thank a lot of funding sources, especially the NSF Fellowship, which got me introduced to the collaborators that I'm working with in the project today. So thank you all very much for being here.